Hello everyone. I've drawn the block diagram for the LED racing game, and it consists of various subcircuits. We have some counters, an add and subtract unit, a circuit to display the player's score, to take the player's input, a timer, and a finite state machine. In order for a game to function correctly, all these various subcircuits need to be working together harmoniously. And to achieve that, we could use a circuit called the clock. And all this circuit does is output a square wave at a defined frequency. So you're just going to have an output voltage that varies from high to low at a set pace. And just how musicians use a metronome to make sure all the members of the band are playing to the same beat, the clock works in a similar fashion for digital circuits. It ensures all the different subcircuits are performing their functions at a pace dictated by the clock. And sometimes, you'll hear the names, maybe sequential logic or synchronous system. And those are circuits that use a clock to function. And various IC chips need the input of a clock. I've drawn two here. One is a D flip-flop, and another is a counter. And anytime you see this little triangle symbol, that means in order for the chip to work correctly, it needs the input of a clock. And so for our game, how are we going to build our clock? Well, a simple and inexpensive solution is to use the all-time classic chip, the 555 timer. And we have the datasheet here. If we just flip through it, it shows a little picture of the chip and the pin layout. Let me flip through it some more. Let's go back one page. We have the functional block diagram. Now, Ben Eater has an excellent video out that describes the operation of this chip when used for a clock, because he uses a clock for his 8-bit computer. And he goes into some detail, and it's very informative, and I highly suggest you check it out if you haven't seen it already. And I'll put a link down in the description. But the fast food version is that depending what our voltages are on pins 2 and pin 6, called the trigger and the threshold, the output here at pin 3 is either going to be high or low. And if we continue on to the schematic, it gives a number of examples of what the 5.5 timer can be used for. And one is the astable operation. And so it has the schematic here of when it's configured for the astable mode. So let's check it out. So we see at pins 1 and 8, those are the power pins. So we stick our ground and our 5 volts up at VCC there. Pin 3 is the output, and here they've drawn a load resistor, which, for now we can ignore, and we could also ignore this coupling capacitor for now. And so let's check out the other pins. Pin 5 is left untouched, so you just leave that open. That's easy enough. Pin 4 here is the reset pin, and this is a kind of an override mechanism that once the reset is engaged, the output is pulled low regardless of what the other pins have on their inputs. And anytime on a schematic, if you see a little bubble like this in digital logic, that means that this pin is called active low. So if we want to reset this chip, we need to send a low pulse to the reset, and that will reset the whole chip. Pin 7 here is called the discharge pin, and this is a very interesting pin. What happens in this pin is that at pin 7, it alternates between an open circuit and a short circuit to ground, depending on the output here at pin 3. So if the output is high, then pin 7 is an open circuit, and if the output is low, well, pin 7 is a short to ground. And pins 2 and 6, as we said earlier, the voltages at these two pins will dictate what voltage, whether the output is high or low. And in this astable mode, these two pins are tied together. And now the three components that we have to add to this chip are resistor A, resistor B, and a capacitor. And so let's go through how this operates here. So let's imagine that the output is high and the discharge pin is an open circuit. Well, you're going to get current coming down from our 5-volt source through resistor A. Now, since the discharge pin 7 is an open circuit, well, no current's going to go down to a dead end, and so it's going to keep on going down here through resistor B. And at pins 2 and pin 6, these are these have a high impedance, and so a very negligible amount of current is going to be drawn into them. And so we could just say that basically the current goes straight down through the 2 resistors and the capacitor, and it will start to charge up the capacitor. And as the capacitor charges up, the voltage across it, and thus the voltage at pins 2 and 6 here, is going to increase. And here they have a little diagram showing just that. So we see the capacitor rising up in voltage. And once it hits the threshold voltage, the output immediately changes from high to low. And once it goes low, at the same time, the discharge pin changes from an open circuit to a short circuit to ground. So if we have ground here at pin 7 and positive charges up on the capacitor here, well, those charges are going to want to discharge through resistor B and out pin 7. So we can call this current ID for discharge and this one IC for charging up. And as the capacitor discharges its current through pin 7, the voltage here is going to drop. And again, if we look at the plot here, we can see the capacitor voltage start to drop down. Now, once it hits its lower threshold, the output is immediately going to jump back high. And when it jumps back high, well, pin 7 here is going to become an open circuit again. And so once it's an open circuit, it's going to recharge from our 5 volts back down through resistors A and B. And these two, and it's going to basically alter between these two states. You see the capacitor charge, discharge, and correspondingly our output voltage is going to go from low to high and low to high. And that's how we get our square wave at the output. And this was going to be our clock signal. Now, it's no coincidence that the components that we need to add to this chip are a resistor and a capacitor. And this is because a resistor multiplied by a capacitor equals time. So ohms times farads equals seconds. And this is an exceptionally useful phenomenon. This means that with these two dirt cheap components, we can essentially have like a little stopwatch for our electronic circuits. And depending on the values of both the resistors and the capacitor, that will determine how long it takes for the capacitor to charge, and essentially how long your little stopwatch is going to be. And they have a couple equations down here. They have TH, which is the time that the output voltage is high. And we see that's proportional to resistor A plus resistor B times the capacitance of the capacitor. And they also have TL here, which is just the time that the output voltage is low, and that's proportional to resistor B times the capacitor. And the reason resistor A is not in this equation is because as the capacitor charges up, it charges up through both A and B. However, when it discharges, it only discharges through B and doesn't bother going through A because the ground is right there. And so that explains the difference between these two equations. So, and that also explains basically the operation of the astable mode in the 5/5 timer. And so let's go check it out on the breadboard. So we've got the 5/5 timer in the astable configuration on our breadboard over here. And for resistor A, I'm using a 1 kilo ohm resistor, and resistor B is going to be a 100 kilo ohm potentiometer. And it's tied up to act just as a variable resistor. And for our capacitor, I have a 4.7 microfarad cap. And you can see pins 2 and 6 are tied together, and our reset is tied up high so that our chip cannot reset. I've also added a little 0.01 microfarad cap on pin 5 that goes to with. And this has been added because the in the data sheet it suggests to add one, as it helps with the operation of the chip. Now we should also add a 0.1 microfarad cap across the power rails. And they had that in the data sheet, but generally for pretty much all IC chips, it's good practice to add one of these caps across the power rails to help have a clean kind of power source. So let's, oh yes, and also as you can see, I have oscilloscope probes attached as well to the output and also to the voltage across the capacitor. So we can see the capacitor charge and discharge. Okay, so we see our square wave, and maybe if I increase the frequency, it'll look a little better. So the purple trace is the square wave, of course, and the other one is the voltage on the capacitor, and it looks just like the diagrams, or the plots I should say, in the data sheet. Now, if we want to get a visual representation of our clock, we could add a little LED. So, of course, a current limiting resistor, and I'll do that right here now. And there we go. So our LED is blinking away, but you might have noticed that the output of our voltage has dropped, and it's only around 3.6 volts, even though it's supposed to be 5 volt kind of logic. And the reason for this is that I've got the old school BJT 555 timer here. It's the NE555. And because of the BJTs and how they function, they have difficulty going straight up to 5 volts. In the CMOS versions, they go from 0 to 5, nice and easy. But because of the BJTs, they don't do that, and so the logic is kind of skewed downwards. You know, it's easy to get a ground at 0 volts. But our high, even though our supplies are at 5 volts, they can't quite get up there. And so that's something to keep in mind, especially if we're using HC chips in the future. And this is our clock circuit, and the frequency can be controlled by this variable resistor here. And it seems to function as it should. Okay. All right, guys. Thanks for watching.